This lecture, I tried to tell you a bit about what we actually see in the Earth's magnetic field, the actual data that gave us information about the fields that exist, and I talked about dynamos in other planets and magnetic fields in other planets. And in the second lecture, I told you a bit about how we construct simulations and also some of the results that come out of numerical simulations, and we started to look at how these sort of match up to what we actually see. Now I want to start talking about the sort of the theoretical framework which actually lies behind the dynamo simulations. This is really all we have to try and explain what we actually see and try and interpret what we actually see in terms of the actual equations. So I think, as Anwar pointed out, in the simulations, all you're doing is integrating these very complicated nonlinear equations, and what you get out may or may not resemble the phenomenon you're trying to model, but considerably more effort is actually needed to try and understand what's even going on in the simulations before we even attempt to sort of correlate this with what's actually happening on the planet. So most of my main sort of aim here is to try and understand, well, limited aim of trying to understand what's actually happening in the simulations in terms of mathematical models which you can actually do. Okay, so this is sort of filling in the gap between theory and simulations. And in the final talk I shall continue this and go on a bit further to try and relate what we're actually seeing to more to what happens in planets. Okay, so a brief outline of what I'm going to talk about here. So I'm going to talk about linear theory of rotating convection. Linear theory is typically far from what we're actually, the parameter regimes we're actually in. It's usually not that far from the simulation regimes, but even in there are strong nonlinear effects. But it is something that we sort of understand reasonably well, and therefore it's a good place to actually begin our investigation. So I'll be telling you a bit about the situation about onset of convection in rapidly rotating systems. There are two methods of approaching this. One is essentially solving the eigenvalue problem numerically, and the other is by asymptotically understanding what happens in the rapid rotation limit, which for linear theory is that E tends to 0, the Ekman number going to 0 limit. And then we'll talk a little bit about how those non-magnetic effects are influenced by a magnetic field. And then I'm going to tell you a little bit about two particular topics which are particularly important in geodynamo theory, which can also be dealt with by fairly simple mathematical models. These topics are the kinds of waves that can actually occur in the core, and that leads naturally on through the torsional oscillation waves, which we'll discuss, to a discussion of J.B. Taylor's constraint, which has played quite an important role in geodynamo modelling over the last 20, 30 years or so. And finally, I'll try to put all of this is what you might call fairly well-established theory. There's a sort of fairly tight mathematical basis for it all. But down here, I'll talk a little bit about how we put together all these ideas to try and develop scaling laws to tell us questions which we really want to know in planets, like in the strongly nonlinear regimes and in situations where the Ekman number is very, very small and the Rayleigh number is very, very large. Can we find estimates of typical velocities in magnetic fields following on from our understanding, theoretical understanding that we've developed using simulations and the asymptotic theories? And this is much more speculative in the sense that there are, as we've heard before, there are different ideas here, and some of the things I say may well be wrong, or at least be overtaken by events later on. But nevertheless, you've got to stick a toe in the water to do here, and that's what I'm going to do there. So that will be the last part of the talk. Okay, so let's have a look at the linear theory of convection to start. So let's first of all look at the simplest problem of the linear theory of the onset of convection. And so basically what that amounts to is finding the critical Rayleigh number at which convection first sets in. So the way to think about these kind of problems is you have your configuration there, you slowly turn up the Rayleigh number until something happens, until convection starts to set in, and you want to find that point. That's the first point to do. And you can also hopefully find out what kind of motions and whereabouts those motions will actually occur. Now, of course, the velocities are going to be initially small when you're just close to critical, so there won't be any dynamo, and so there won't be any magnetic field. So the natural place to start is in the non-magnetic rapidly rotating limit. And, of course, this problem is a long history. The non-rotating case is an even longer history of Rayleigh-Bénard convection. But here the key parameter is this Ekman number here. The gap width being defined as usual. I thought I'd just go straight to, we've seen this picture before, but I'm just showing you it again just to remind you of the geometry of the situation and the notation that I'm using. So the rotation vector there, omega, which is in some sense going to be large. The gravity is always towards the centre of the planet. The z direction is going to be parallel to omega. The s direction will be perpendicular to the z direction. And I'll also be using the spherical polar coordinates r, theta, and phi before. So let's just go back. So that's the geometry we're actually interested in here. And as I say, the main interest focuses on the pattern of convection that occurs at critical, because it appears that that actually persists to quite high Rayleigh numbers. It certainly persists right through the range of simulations that we're going to be doing. Effect of magnetic field on convection is also very important, because that gives you a guide as to when the Lorentz force is actually going to come in and what it's going to do. And as we'll see, particularly I think in the final lecture, I'm going to do lecture 4, we'll show how the magnetic field itself can strongly affect the dynamo properties of the convection and lead to subcriticality and all sorts of rather complicated things like that. And that will be discussed in the final lecture I'm giving. Okay, so let's go. So we've seen that. Okay, so now let's think about how you go about solving the problem of the onset of convection with rapid rotation using numerical methods, first of all. Now, this is a much simpler problem than a full simulation, because we're going to drop nonlinear terms. But nevertheless, the sort of standard approach is the one that's been generally often used here. So as we had in the last talk I gave, we're using spectral methods to investigate what's numerically small but finite e. So we're not going down to the very limit here. We're going to, and it's possible to get down to, say, 10 to the minus 7 without much difficulty. And then the second method is to develop an asymptotic theory that's valid in the e tends to 0 limit. And that's quite a challenge, which we've only really solved at the beginning about 2000, period 2000 to 2005. Okay, so let's go for this one first of all. So as usual, we decompose the velocity field into toroidal and poloidal components, and we insert that into the curl, the double curl of the momentum equation. That's the r component of those two things, yeah. And we're going to scale time, the viscous time scale now. We've got no magnetic field, so eta doesn't appear at this stage. So this is, of course, the natural thing to do. And we end up with these equations here for the linearized equations for the toroidal parts and the poloidal parts. Okay, so let's just have a look at these equations. So this is the radial component of the curl, and this is the radial component of the double curl there. And down here we've got the temperature equation. And I've used the fairly standard nonlinear scaling, which we discussed before. So I won't go through that again. So we've got an Ekman number here, and we've got a Rayleigh number out here, and we have a Prandtl number up here and down there. So those are the dimensions, parameters in that. I'd just like to draw your attention to one or two things here. there's this rather awkward operator. The L squared operator is rather nice because that's just the horizontal part of the Laplacian operator. So if we're going to expand in spherical harmonics, which we usually do, then L squared acting on a spherical harmonic just leads you to L into L plus 1 times that spherical harmonic. That's a very nice formula there. This one is slightly more complicated. This is C for the Coriolis operator. And it's this one here which couples the poloidal parts and the toroidal parts. So one thing we see straight away is that rotation couples the poloidal and the toroidal components of the flow together. And if we didn't have that Coriolis term in, then we wouldn't actually have any such coupling. We could solve for poloidal and toroidal flows separately. And in fact, actually, since the Rayleigh number only drives the poloidal flow, the toroidal flow would actually come out of the problem altogether. But that doesn't happen when you've got rotation, because that couples the two things together. So we have essentially three equations for toroidal, poloidal, and temperature fluctuation. And these are linear equations, because we've dropped all the non-linear terms, and we have to solve these. And there are two standard cases, perhaps the most commonly solved. Certainly historically, the first one to be looked at was the internal heating. That's where the whole sphere is driven by a uniform internal heating. And the differential heating, which corresponds to the case where all heat flux, input heat flux, is going through the inner core, and there's no heat flux actually being input into the sphere itself. It's all just coming in, and then all just coming out at the top. And that leads to the same sort of equations, but here we have a 1 over r cubed, whereas we have the opposite. Slight technical difference, but one code, of course, is capable of dealing with both of those. So here we have the definitions of the Ekman number and the Rayleigh number and the Prandtl number, since we've discussed those before. I don't need to go any further with that. So we can expand our poloidal parts, our toroidal parts, and our temperature fluctuations in terms of spherical harmonic expansions, as normal. Of course, now, because it's linear, we know that the time dependence is going to be like e to the minus I omega t there. So that's helpful. And the different m's are all completely decoupled from these equations. So the Coriolis operator couples together various components of these together, but it doesn't couple together different m's. So all the different m's can be solved one after the other. So we can think of m as an input parameter, and then you can minimize the Rayleigh number over that particular m. So typically you've got a program there, you try running it at a particular value of m, and you find out a Rayleigh number, then you try a different value of m, and maybe you get a smaller Rayleigh number, and you hunt around in m's until you get the smallest Rayleigh number that you can. That's the first one that actually comes in.
This T0 of R is correct?
Sorry, T0 of R, yes, that's the basic state temperature profile. Yes. So that's the basic state solution. That's the solution of del squared T equals naught in the case of differential heating. Yeah. So that's just got a 1 over R squared and a constant term, which then match up to the boundary conditions. In the case of internal heating, dissolving del squared T naught equals constant. Okay. And that gives you a slightly different solution, but in either case it's just purely spherically symmetric, and they're just very simple. Really. So it's very easy to work that out.
Chris, may I ask something?
Yeah.
You have a very high order of the equations. You need a horribly large number of various boundary conditions, initial conditions.
Well,
is it easy?
It actually turns out to be very nice. Actually, it's one of the nice things about spectral methods. I think I've probably got a little bit about it later on. But basically, you need two conditions on the poloidal part, yeah, two on both boundaries. That is to say, it's a fourth order system in the radial direction in P. So you need two conditions, one of which is always just P equals naught, that's no penetration through, and the other one depends on whether it's stress-free or no slip. Yeah? And then you have one condition on the toroidal, which again depends on whether it's no slip or stress-free. It's either T equals naught or the derivative of T equals naught. Yeah? And then on the temperature boundary condition, well, you usually assume in these sort of analytical type work, you usually assume that it's constant. So it's like Rayleigh-Bainard boundary conditions.
So Do you you normally have, of course, maximum two derivatives, but for the Lorentz force, do you have three or also only two?
This is non-magnetic at this stage.
Yeah.
So when the magnetic field comes in, you normally have two extra ones, two new boundary conditions. One essentially for what corresponds to the toroidal component, and another that corresponds to the toroidal component.
And the maximum derivatives?
It's
the Lorentz
fourth order in P, it's second order in this toroidal here, it's second order in that, and both the magnetic fields are second order and second order. So
Yeah, but how many derivatives?
10 altogether, I guess.
Yeah, but how many derivatives do you need? I mean, what's the largest derivative on each function?
On each one,
Is it two or
the
three?
fourth in P, that's the largest derivative that actually appears in the colloidal
The
equation.
fourth derivative?
Yeah, if you in the radial, if you just hang on, if you just go back a second, yeah, it's there. So L squared is horizontal, so that doesn't introduce radial derivatives, that just gives you an n plus 1, so there's one del squared there, another del squared there.
Yeah, but you invert this operator again. No?
Well, that's part of the solution, of course, is inverted.
Or maybe you don't, yeah.
Right, okay. Well, when you insert these expansions in, essentially what you end up with is a matrix eigenvalue problem. The d by dt's all produce an I omegas, and all the other ones produce some other matrix there. And x there is to be thought of as a long vector, and it's composed of all the harmonics that we get in front of these coefficients here. So if we're going to expand that in terms of Chebyshev polynomials, this will be in n Chebyshev polynomials, you have pln, you also have a tln and a t prime ln. You run all those variables together, so it's basically a 3 times n times l system of the vector system there, and then that's a big matrix. Of course, these are two big matrices there. And basically you solve those matrix equations for eigenvalue, and you look for the case when you get a real value of omega there, because that corresponds to something which is neither growing nor decaying. That's the neutral case. And the eigenvalue, it turns out, tells you the frequency with which the system is actually moving at onsetting or minimizing, as I said before, over n. Now, there's something which makes this much, much simpler than it at first appears, because it looks as though this is sort of quite bad news, because this is an n by l by 3 vector, so it's n times n, l times 3 all squared is this matrix. So it's a big matrix. But the nice thing is that Coriolis operator only couples P2L to P2L plus 1 and P2L minus 1. And that means that although this matrix is big, it has a bounded structure, and as you probably know, there are very efficient algorithms for finding eigenvalues of bounded matrices. So you can actually go up to quite a large number of radial Chebyshev polynomials, quite a large number of spherical harmonics, and still solve the whole thing on a machine that's not much bigger than this.
But, Chris,
yes.
Of course the accuracy of spectral method is higher, but still 50 by 50 for finding different schemes doesn't seem to be very high resolution, right?
Yes, that's true, but these spherical harmonic things work better than that, because for a given value of E, once you've got up to a certain number of harmonics, then it decays exponentially. The amplitude of each harmonic decays exponentially in the solution. So once you've got enough for resolution, then it gets really, really accurate. So it is actually possible, certainly for these linear type of problems, you can solve these essentially to 6 significant figures if you want to. It's that accurate. But I mean, that's because it's linear. I mean, I'm not claiming that our spectral methods will produce answers for non-linear problems which we write to 6 significant figures, but certainly for these linear things it is. Yeah. Okay. So we have these bounded matrices.
Question, yeah?
Yeah? Sorry. Yeah?
With boundary conditions, the non-Stefan stress-free, does that still leave you with a bounded matrix?
Yeah, that's sort of right. But actually, the boundary conditions that we normally apply actually still leave you with a bounded structure, actually, because they're so simple. The P equals 0 and the T equals 0. In more general circumstances, what I do is having got that matrix, I basically reduce that matrix using the boundary conditions. so that I have extra variables. So instead of actually expanding up to from 1 to n, I expand, say, from 1 up to n plus 4, and then I get from n plus 4 down to n using those boundary conditions. So that's, and then I get what I call a reduced matrix, and then this then applies this reduced matrix. So that's basically what I'm doing. So that, of course, isn't a huge amount of work because there are only a finite number of these boundary conditions. So it doesn't actually slow the thing down all that significantly. Okay, so right. So this is the kind of solution that you get. This picture was actually supplied to me by Emmanuel Dormy, and I like to show this because it's such a pretty picture. Let me explain this picture. So this is what the nature of the eigenfunctions which turn up. That's the nature of the solutions that turn up when you solve that ax equals I omega bx. That gives you the kind of x's that you get. So you get all the components of the toroidal, colloidal, and temperature fluctuation. And this is a plot. These things here, these columns here, is actually axial vorticity, which is actually plotted here. So it's measuring the strength of the axial vorticity. Inside here is the tangent cylinder there, so that you can see that the solutions are turning up with solutions which onset close to the tangent cylinder. So the onset of convection, in this case here, is close to the tangent cylinder. You can see that the structure is columnar, very strongly columnar. You can see that as the Ekman number gets smaller, the columns get thinner and thinner and thinner. And that's a general feature of this type of actually what happens when you solve it. So, of course, as you try to get smaller and smaller E, the resolution, it becomes more and more difficult because you can see that finer and finer structures are occurring. So you do need more and more polynomials, that's quite true. So you can never get down to tiny, tiny E's using these types of methods because the structures, the spatial structures get too small. Okay, and there's another point. Yeah?
There's caps at the top?
The caps, oh yeah, that's the sphere. Yeah. Remember, so we're in a spherical geometry, yeah? So these columns are doing the best they can to be columnar, but of course they can't be quite columnar because they've got to fit onto those boundary conditions at the end. And so the flow, these flows, that's the flow pattern there. So you can see it sort of spirals also. It's not just a simple going round and round like that. It's coming out like that and then going back along like that. So there's also the spiraling. That spiraling is extremely important when you're discussing the creation of zonal flows, because zonal flows are actually produced by this spiraling. If this thing didn't spiral, if it just came straight out and straight back, then that wouldn't actually drive any zonal flows, and that's the origin of things like well, basically it's the origin of most differential rotation. I mean, it's the origin of the strong jets on Jupiter, it's the origin of the fact that the sun rotates faster around the equator than at the poles. I mean, it all basically comes down to this, although of course it's much more complicated in these things than many, many other effects going on, but basically that is the principal driver. These things are producing Reynolds stresses, and those Reynolds stresses are driving zonal flows. So the spiraling is rather important. Other thing that's rather important is the symmetry of this solution. I haven't actually talked about that. Yeah, okay. So, oh yes, I did. I should have mentioned that at this stage here. The symmetry of these solutions, you can see from that solution that I just put up that the omega z is more or less constant right along the column. So that means, of course, it's symmetric about the equator. And then if you think of it, that means that the radial velocity is also symmetric about the equator, and so is u phi. That's the azimuthal velocity is symmetric about the equator. But uz and u theta, uz in particular is the velocity up the columns. That is antisymmetric. So what you can't really see in this picture, which is perhaps a bit of a pity, is that not only is there's an omega z like that, but there's also a flow going up there and down there and up there and down there. So that in these columns there's also a vertical flow going on, z flow going on, and it's up in one direction. Each column is in one direction, up in the northern hemisphere, and in the opposite direction in the southern hemisphere. And these solutions have exact parity, so this is it's exactly, the UZ is exactly 0 at the equator on the solutions. And then there's another family of equations which have the other parity, the opposite parity of that, where UZ is essentially constant as you go, well, 0 there, but it goes up to a big maximum there and then it goes down. So the UZ is symmetric in the other parity, and then only UZ is antisymmetric, so it's got the opposite parity. For those of you who are interested in history of science, Paul Roberts got essentially the asymptotic theory of rotating convection sorted out in 1968. He made one mistake, and the one mistake he made was to get the wrong parity. That is to say, he thought that the most unstable mode would be the one where Z had the same sign, which is of course the same as happens in the Rayleigh-Bénard convection. Fritz Busser fairly rapidly pointed out the error in 1970 and pointed out that you actually get a lower value of the critical Rayleigh number with this parity of solutions. And the power of pictures is such that it's always Fritz's name that is remembered, Fritz Busser's name which is remembered in connection with this, despite the fact that Paul actually worked out the entire theory, essentially exactly the same theory, for the opposite polarity mode, and that was the only thing that was wrong in his 1968 analysis. There you are. So don't forget the power of the picture. That's the message to the young. Okay. Okay. Oh, this is another picture. This is a horizontal. This is an equatorial section. Yeah. So this is a section across the equator, and yeah, this is at 10 to the minus 7, which is a fairly low value. And it's similar to the other one. Again, we're seeing the axial vorticity. This perhaps shows you the nature of the spiralling, perhaps a little more clearly. And this also shows you how good the asymptotic theory that I'm going to describe in a minute is, because these are the ones that come from the asymptotic theory, these are the ones that come from the numerical theory. And at 10 to the minus 7, he is sufficiently small that it used to be, you've got to look fairly closely to see the differences. This one is for differential heating, where it comes in close to the tangent cylinder, wherever the tangent cylinder is. This one is for internal heating, and in order to get that close to the tangent cylinder, you need to have a fairly large radius ratio. So if you have the Earth's radius ratio, you would see just spirals coming in somewhere in the middle. Yeah. So, right, so what about the asymptotic theory? Because for the mathematicians or the mathematically inclined, this is the sort of the most interesting part. This is the how does this thing actually work in the limit of very small e, and it's also a practical question too, because the e in the Earth's core is 10 to the minus 15. It's way below where you can get even on linear theories of numerics. So, so we have to understand what's going on asymptotically if we're going to get to Earth's core values. And, of course, you look at those pictures that we have from the numerics and you say, well, the obvious feature of them is that the derivatives in the horizontal direction are much larger than the derivatives in the vertical direction. In the vertical direction, there's hardly anything happening. The columns are extremely tall and thin. And so one takes that scaling as order 1 and that scaling as order e to the minus 1/3, and that's a big number. So this is very like what Anwar was telling us at 11 o'clock, except it's exactly the opposite. Anwar had this large and this small, I've got this large and that small. So that's the very important idea. So you apply them, this kind of asymptotic applies to be applied to the Earth, the Sun, the galaxy. It's just a question of looking at it in the right way. Okay, so then we get these relations here. And so then we get these equations here, which are now essentially the same as the previous ones, except these are the cylindrical polar coordinate versions of the previous ones. And those are the equations which actually determine. Now, I've not made any assumption about E in particular here, except that I've used this to drop places where you get smaller derivatives, smaller order derivatives, so these are the leading order derivatives in that equation. Then the higher order term we've gone what this comes down to is basically what's sometimes called quasi-geostrophic. Quasi-geostrophic essentially means that the derivatives from there, which would occur in the S and R directions, are neglected, so that we only, from this part here, we only just get that part there, and this part here just leads you to that part there. So that's basically what happens in this tall, thin column approach. Okay, so we've got these nice equations there. What do we do with them? Well, we can scale E out of the problem. So that immediately tells us that there is an asymptotic limit at small e. And the scalings will also tell us what sort of Rayleigh numbers and so on we're actually going to get in our system. So we now know straight off that r, little r is going to be, curly r is going to be order 1. So that tells us that the critical Rayleigh number will be very large. So rotation is delaying the onset of convection by a large amount. The faster it's rotating, the more it's delayed. That gives us the frequency, the drift frequency of the thermal Rossby waves, which are the kind of modes we're actually seeing. That gives us the azimuthal wave number. Immediately explains this picture over here, because you can see that if little m is order 1, capital M is then large, so small e, you've got lots and lots of columns. Remember the picture, we just go back to the Dorney picture, lots and lots of columns at small e. So that's exactly as the asymptotic theory predicts. Yeah, so that's that scale out, and then these other scalings, well, I'm not going to go on about those. Now you put all this in, and what do you get? You get this equation, which I call the Roberts-Busser equation, since it was derived both by Paul in 1968 and by Fritz in 1970. That's the appropriate name to call it. And this is just a simple second-order equation in Z, which describes the structure along in the Z direction of this, these columns. So this tells you, this is actually the vertical velocity, so that gives you a simple equation for W. And then you've got 2-point boundary conditions there, which are essentially the no penetration conditions, so there's no flow through the end there on those boundaries. So that's the very, very simple problem that you actually have to solve.
Would it be, does it mean anything meaningful if I go further and completely neglect d by dz? So then I will have just the term with the square brackets equal to 0. It's an infinite column.
Can't do that. Can't do that. Can't do that. You'd lose the effect of rotation altogether if you did that. Because basically, this thing here, yeah, is important because it's telling you that the boundary is actually sloping. Yeah? If the boundary was not sloping, if the boundary was flat, then you could have an exact balance of Coriolis force versus pressure, and rotation would do absolutely nothing at all. You would only just balance the pressure force throughout. It's the sloping boundaries which is absolutely crucial in this thing. So the sloping boundary condition here has got to be imposed, and that means you've got to have a 2-point boundary value problem. You've got to have d2w by dz squared, otherwise you won't get anything sensible at all. So all this, as I say, is essentially what was in Roberts and Busser, and you've got to solve this. You can think of this now as a dispersion relation in terms of S, K, M, and R. Now, M is the Rayleigh number, that's the scale wave number in the S direction, and that's the actual local value of S. That's where you actually have, which is normally the tangent cylinder value if you are on the set close to the tangent cylinder. But not, of course, it isn't. So, natural way to proceed, which is what Roberts and Busser actually did, is to enforce omega real and minimize R over M, K, and S. And that's what's sometimes called the local theory of the onset of convection. And it gives the right answer when convection sets in at the tangent cylinder. So in those pictures I showed you, which were carefully constructed actually so this was true, then that does actually give you the correct answer. So that simple way of doing it gives you the correct value of the Rayleigh number and the corresponding value of n. So that's all fairly neat and fairly straightforward. The thing which caused the gap between 1970 and 2000 was trying to understand what happens in the internal case, because then you need WKBJ solutions which decay to 0 in both directions away from the critical cylinder. And this is something which Andrew Sauer and I worked on for some time, and eventually we managed to solve it, but only after a long, long time. So basically what you need to do is to find a point SC in the complex S-plane. And at that point you have to have the group velocities going to 0, and you also have to have the phase mixing going to 0. So mathematically it looks rather pretty. You've got these two equations here for the dispersion, from the dispersion relation, and it's this one here which causes all the difficulty, because in the local theory that one turns out not to be 0. If you just do local theory and calculate d omega by dz, it turns out it's 0. And yet you've got to make it 0. And the only way you can make it 0, we finally realised, is to go to look in the complex S-plane. Now that seems a very curious thing to do, because S is a coordinate here. I mean, you wouldn't actually think of wandering off into the complex value of something which is actually a distance from the axis. It doesn't sound right, but it is in fact the only way to proceed. So then to find this SC that's in the complex plane, then we have a recipe here, which are essentially these 5 equations. So we have 5 equations, 5 nonlinear equations for 5 unknowns. And to cut a long story short, you just go ahead and solve these things, and you end up with the critical wave number, the critical Rayleigh number, the critical frequency, and the real and imaginary parts of this SC. And those are not really physical things, that's just a point in the complex plane. But these are all physical quantities which are relevant to the solution. And the Rayleigh wave number turns out to be 0.
Sorry, but then if SR and SI don't have clear physical meaning, how you will decide where the eigenfunction maximizes?
Well, wait 2 slides. 2 slides in time, about 3 years in. Okay, right, so there's the amplitude equation looks like that. So what we're looking for is an amplitude equation which varies as a function of s. That's now the scale value of s, and has a WKBJ type form. And this k here now becomes a function of s. So this is the thing which will be crucial to answer your Feinberg's question. The amplitude equation is that in the neighbourhood of this double turning point, this complex SC part. And this thing has parabolic cylinder function solutions which decay away nicely to 0 as x goes to plus or minus infinity. So you've got localized solutions in the middle, decaying away correctly on both sides. If you don't have d omega by ds 0, you end up with an x term here. Airy functions are a consequence of that. And airy functions have a horrible property that they can be 0 on one side and they go to infinity on the other, or 0 on one side and infinity on the other, but you never get anything that goes 0 on both sides. So if you've got an x w d omega by dz s, you're stuffed. You'll never actually find a solution of that thing. And that's really the critical point. That's the real reason why d omega by ds has got to be 0. You won't get solutions which decay away to 0 on both sides unless d omega by ds is 0. And it also gives you the sort of scaling of x as well, which is e to the 1/6, which is small, of course, because e is small, but it's not that small. So that's why you have to go to rather low e's in order to see good agreement between asymptotics and the theory. Okay, now let's see. And so we solve that equation. This actually gives you the correction to the Rayleigh number, so not only you get the leading order R, C, and omega, you also get corrections to this. And because this is an eigenvalue problem, there's a whole sequence of these things. So there's a whole bunch of modes with different radial structure which come in all very close to RCs. So once you've gone through the RC threshold, there's quite a lot of complications would come in. The higher eigenmodes start to come in quite quickly, because that's quite small.
So it's all analytically parabolic. It's parabolic cylinder.
Yeah. The parabolic cylinder thing is solved analytically. That's right, and that gives you that has the values of 1, 3, 7, 5, 7, etc. And that it all checks out with the numerics. So I mean, basically, all those codes, I found every single mode that corresponds to all the first 4 modes. I think I checked out, and they all agree exactly. That's how we know it's right. Now, Anvar's question is, how do you get all this back to the real axis? How do you find out where this thing actually occurred? Where is the maximum amplitude in that? Now, you have to think now, we've got the omega c from the turning point theory forget about all the other dependencies in there because they're all determined, and we've just got an omega, which is a function of s and k. And s can be complex and k can be complex. You move around on the complex plane, so you can fiddle around k's so that s becomes real, and that's what you have to do. So basically, you've solved this dispersion relation now in order to get k that comes out for a given real s. So as you move along s along the real line, so you then get out a k from that dispersion relation, and that k has an imaginary part, and on one side it's growing, and on the other side it's decaying. At one place, the imaginary part of k is 0, and that's where maximum amplitude actually occurs. If you pop that back into the WKB approximation, you can see that counts. So the nature of the solutions is essentially an oscillation which grows, and then an oscillation which decays. And the place where it's located is the place at which that actually occurs. And that's actually significantly different from the local theory of prediction. This is Busser's famous 1970 picture, and it's not all that different from the picture that we're getting out from this theory. It's perhaps rather a shame that after all this huge amount of effort, the final answer is not all that different, but there is a difference. When Fritz did this, he actually, if you look closely, he very carefully drew it so that that radius there, that s there, is almost exactly 0.5, which is the local theory prediction. The global theory prediction gives you that s is 0.6 rather than 0.5. So the real thing should be just slightly further out than Fritz's original prediction. But it's not a huge difference, to be honest. But it's a huge difference in conceptually and theoretically, even if it's only quite a small difference in actual numbers. So that picture is not quite right, that famous picture, but nobody ever bothered to draw it again because you wouldn't be able to tell the difference between one numbers of 0.5 and 0.6. That's that. Okay, so, and the final little twist in the tale is about when all this is valid, and you have to have this is something like Stokes lines. Those who are interested in WKB methods will know about these things. Those of you who don't can look them up. Okay, so that's the sorted the theory of the offset of convection. Yeah. Yeah.
Given with all the refinements, how much above critical do we think?
What's the change from the local theory? It's about a 20% change. It typically, it depends a bit on the Prandtl numbers, actually, of course. But if the Prandtl number's if the ordinary Prandtl number's about 1, then it's about, the global critical is about 20% typically higher than the local, which isn't very much. But,
so the real Earth is still...
The real Earth is governed by the asymptotics. I mean, all the local theory and the real theory have the e to the minus 4/3 factor, which is huge compared to these 20% that I'm talking about there. So, I mean, in a sense, this doesn't make a huge amount of difference for the Earth, really, because we don't know anything with that accuracy. But it's interesting to get it right, isn't it? Okay, so now this is perhaps a little bit more physical here. This is what the effect of a magnetic field is. So there are several effects of a magnetic field when you impose that. The simplest problem to do is what's sometimes called a Malkus field. That's a magnetic field B, which is azimuthal. It's only got a phi component, and its strength goes linearly with the distance out. So that B is proportional to S. And you might say, well, why do we bother to look at that? Because that's got a quadrupolar type symmetry. The Earth's field and the solar field have got B phi's which are anti-symmetric about the equator. This is symmetric about the equator, so it's got the wrong parity. And yeah, that is quite, well, as we'll see in the next talk, that is actually quite a serious objection. But the reason we did this is because it's a computational reason, really. If you have that particular magnetic field, you still keep this lovely property about coupling adjacent spherical harmonics. You get magnetic operators like the Coriolis operator. If the magnetic field has that form, you only couple adjacent spherical harmonics, so you end up with a bounded matrix, which means the whole solution goes much, much faster and you can get much, much higher resolution. You can do other V-naughts, of course, numerically, but you will have to, it'll take a much, much longer time, and you won't get answers that are anything like as precise. And that's the reason why people have concentrated on that field first. Okay, so what happens then? So we've got an azimuthal field, it's threading through those convection rolls, and of course the convection rolls, it doesn't really like that because you're churning up magnetic field, and also this length scale here is quite small, so you're actually cutting across magnetic field lines transversely. And what is the response of the flow to not liking that? The response of the flow is to go to a lower value of m, a larger azimuthal wave number. So the very, very thin columns can be broadened out by a magnetic field. And that's true of B phi too, and it's also true of Ez. So whether you have a vertical or a horizontal field, that still broadens it out. As you might imagine, the azimuthal one, which cuts directly across them, is more potent. You only need a smaller V phi to turn that into that, whereas you need a stronger Vz. In technical terms, you need a field of Elsasser number 1 if it's a vertical field. You only need an Elsasser number e to the 1/3, which is considerably smaller if it's cutting that line, cutting those lines across. So that's the first thing that a magnetic field does. It sort of reduces these tiny thin length scales, and that's sort of quite important actually, because e to the 10 to the minus 15 is so small that if the cells were really on e to the 1/3, it would be embarrassingly thin. They would only be about 100 meters in the Earth's core. And can you really believe you've got a column 100 meters wide going 2,000 kilometers? Well, maybe if you're a theoretician. I think if you're anybody else, you'd have a lot of trouble with that. So the fact that the magnetic field opens these things up is somewhat reassuring. Okay, magnetic fields can also reduce the critical Rayleigh number. So this is the typical plot of the critical Rayleigh number. As you increase the magnetic field strength, typically it goes up a bit at first, and then it goes down very considerably. And that's basically because we're breaking what's sometimes called the Proudman-Taylor constraint, or sometimes the Taylor-Proudman constraint. So what is that? Let's just talk a bit about that. Oh, no, sorry. Let's go back a bit here. Yeah, so I'll just go back here. So we've seen what the magnetic field does. It can increase the azimuthal geometry. Yeah, it can reduce the critical value of m. It can also reduce the critical value of Ra by the Lorentz force, counteracting the Proudman-Taylor constraint. Probably most of you would think it's called the Taylor-Proudman constraint, because that's been the usual way around for a long time. And a few years ago I was talking to Raymond Hyde, and Raymond Hyde pointed out to me that actually Proudman's work was first, Taylor's work was second, so it should really be Proudman-Taylor, but there's more to it than that. I'll just tell you this story because it's quite instructive. At the beginning of the 20th century, theoretical fluid mechanics was in pretty poor shape. I mean, the main predictions of theoretical fluid mechanics were that aeroplanes can't fly, which was a bad start. There was no understanding of Osborne-Reynolds' famous experiments in pipe flow, where you got the turbulence. I mean, the simple theory suggests you get Poiseuille flow, and nobody knew about the instabilities that occur, and so on and so forth. No mathematical theory was available at that time. So by and large, it's fair to say that when Proudman produced his famous paper saying that slow, steady motions in a rapidly rotating fluid would have to be columnar, that is to say independent of Z, I don't think anybody believed him. And indeed, if you read Taylor's paper, Proudman was 1917, Taylor's paper was 1923, it's quite clear that even G.I. Taylor started out from the position, well, it might not be interesting to see why this crazy theory is wrong. There was never any suggestion at the beginning that this crazy theory could actually be right. But Taylor was completely astonished when he actually did the experiment to find that actually the theory was correct, and that in fact rapidly rotating column flows do actually move in a columnar fashion, and these kind of columns that we've been seeing in those pictures really actually occur in nature. They really happen in real experiments. not just in mathematical theories.
So did he write this in his paper that he didn't believe
Yes,
it?
it's very interesting to read. It's very interesting to read Taylor's paper because I mean it comes really strikingly comes across actually if you read his paper.
And that's 21,
how
yeah.
surprising it was to him that it actually did this. So that's why I think Crowding ought to come first because he made this remarkable theoretical prediction which turned out to be correct.
The Taylor movies are available on the web.
There's some very nice pictures where essentially you have a little bump at the bottom of a rotating fluid. You tow the bump around here, and the whole column of fluid moves around. You put ink in the fluid to make it visualised, and the whole column of fluid moves around as you do it. Yeah. I'm sufficiently old, actually, to have seen G.I. Taylor himself talk about this, and he actually brought along the apparatus, which was all made out of Meccano. You wouldn't believe it. Well, that's the way things were done in those days. Moved on a bit since then. Okay, so that's all that. Yeah. So now I wanted to talk a little bit about waves in the core, which is a natural development of this. So we've already sort of thought a bit about Rossby waves. So let's now think about taking those equations that we have, the convection equations, and instead of actually solving it in a global situation, let's just suppose we're locally at one little point, and we'll just look for wave motion. So locally, we're at constant temperature gradient, you have constant magnetic field, and you're just looking for solutions of that particular form, and you look for solutions of that particular form, and what sort of dispersion relations actually come out, what relationships between omega and k you actually get, and that's an extremely instructive thing to do. So if you do that, then the linearized equations just become this. So the linearized version of the momentum equation, the Coriolis term is linear, of course, the buoyancy term, which is linear. You have to have a fixed B naught, the small perturbation J comes in there. You don't usually considering situations where there's no J naught here, so you usually just look at that. And then there's a small viscous term, and the induction equation simplifies it in these fashions here. And I'll always take the vorticity to be the curl of the velocity. Okay. So the first thing you can do is to take the curl and double curl as usual, and z components, and that will give you these two equations. And you then can eliminate, putting the ETIKX formula into there, you end up with this dispersion relation here, which is the dispersion relation for inertial waves. And physically, the way to think of this is that the rotating fluid is permeated by vortex lines, vertical vortex lines. These vortex lines don't like to be bent, so when you do bend them like that, they spring back like that, and they start wiggling backwards and forwards like that. So they're essentially vortex lines which don't like to be stretched and therefore vibrate. And the main properties of this thing can be actually deduced straight off, because clearly if you have a motion which has a small kz like that, then that's stretching the vortex lines a lot, so then you get a high frequency. If you have a kz which is small, i.e. not much dependence in the z direction, then the waves are comparatively slow. And that's why the thermal Rossby waves are actually considerably slower than the rotation rate. Okay, so that's inertial waves, typically fast periods, typically days. And do they happen in the core? Probably, but we don't really know, because the magnetic field will be shaken up on such a short time scale, it would diffuse away before it ever got anywhere near us. So it's extremely hard to detect that kind of motion, that kind of frequency, actually in the Earth's core. But it's almost certainly there, and it's certainly found in all the rotating lab experiments which are done. So Dan Lathrop has a rather nice sort of, he sort of translated the thing into actual notes that you can hear, and you can sort of hear a sort of little symphony coming out of an experiment where all the frequencies corresponding to these various waves are actually present. So the tall, thin columns where K is only used to half, that's the limit we were discussing before of velocity waves, and they're small and they're quasi-geostrophic. Motions with very small k usually are exactly geostrophic because they have Coriolis and pressure forces. Okay, so there we are. So we may have inertial waves in the core, we just don't really know. So what about Alfvén waves? Well, of course, if you just ignore the rotation for a moment, then we can get these kind of Alfvén waves. This is the Alfvén dispersion relation, and that will happen in the core too. This time period turns out to be about 50 years, which is much, much longer than the inertial time, which is only a few days. So, of course, this means that the Coriolis forces are in some sense stronger than the magnetic forces, so that we'll only see these periods of about 50 years, provided omega dot k is small. So these in only waves with omega dot k 0 can have periods as slow as this. These waves are therefore known as torsional oscillations, and they correspond to a whole cylinder of fluid rotating backwards and forwards, with magnetic field permeating that, so the restoring force is the magnetic field when you stretch it out. It doesn't like to be stretched out, it tries to get back, and it goes around like so, and it has to be at kz equals 0, so the whole column of fluid has to move around, and in order to get a proper motion which has no kz anywhere, you have to be on a sort of geostrophic contour, which means you have to be on a cylinder, basically, where the height of the whole column is the same. So that's why you get
the same physical nature of the torsional oscillation of the sun?
That's an interesting question. Not quite, I think, because in the sun you don't really have this dominance of rotation, do you? So you wouldn't expect. I mean, there are waves about 11 years, aren't there? But I don't think you'd expect those to be independent of Z, because there's lots of viscous, turbulent stresses and so on going on in the sun, which are negligible compared to these things in the Earth. So it's sort of like it. I mean, it is basically the same in dynamics, but it's more complicated in the sun because there are extra terms you can't really ignore the number of stresses. Whereas, I mean, as we said in the Earth, all the velocities are very small. Remember, it's all moving at snail's pace in the core, slightly slower than snail's pace, so that the inertial turbulent terms are much, much smaller than these Coriolis terms in that situation. So it is a bit different. But I mean, the basic physics is the same. I mean,
But these are real Alfvén waves, no?
yes.
Yeah, because the torsional oscillations in the sun,
well, not.
they are not that. They are just a response to the magnetic field, at least according to what most people believe.
Yeah, and even they're sort of controversial as well, because I mean, some people believe they're mostly thermal. Not all. But anyway, I don't want to get into
Not all?
We can discuss that at the end, but I mean, that's a bit of a distraction here. Because the good news is that these torsional waves are seen in the Earth. If you look at geomagnetic data, there's definite evidence that these things are actually happening, and people have actually plotted these. This is a very active area of research to try and model these kind of torsional oscillations and develop a picture of what's actually happening in the Earth's core, and actually work out, possibly manage to work out what the magnetic field is by looking at the periods of these torsional oscillations. So that's, unlike the inertial waves, which are too short, these things come on a time scale which is sort of convenient. And there's one other wave which was sort of introduced, I think, by Brzezinski a long time ago. And these waves are waves where the Lorentz force and the Coriolis force are in balance. So these are sometimes called magnetostrophic waves, which are the balance between these three pressure, Coriolis and Lorentz. And the only time derivative comes in here. So these are inertia-free. So unlike the Alfvén waves, torsional waves, where the inertia is important, these waves here are on a much, much longer scale, and everything is adjusting hydrostatically, so it's in continual balance as this moves around. And these occur on this is Alfvén time squared, frequency squared divided by the very short Coriolis frequency, so that turns out to be a long time, that's a period of over 1,000 years. And this is about the kind of frequency that you get with reversals and excursions of the magnetic field. So another way of thinking of those reversals and excursions are that you're exciting slow magnetostrophic waves inside the core, and sometimes those oscillations get big, and sometimes they can need to reverse it. So it's another way of thinking of that operating inside the core. So those are the waves. And again, Brudzinski and her student Makelis in the 1990s did some work which was proved to be quite influential and has gotten a lot of thinking in this subject. He pointed out that if you want slow motions in the core, they better have omega dot k equal 0, and they better have b naught dot k equals 0. So if you've got really slow motions, they've got to have wave numbers which have got satisfying those relations. Small-scale turbulence in the core is more likely to occur if the k wave numbers satisfy those relations. His argument was that if they don't, they will lead to fast oscillations, and those fast oscillations will radiate away and lead to dissipation and damp out. That's perhaps not so clear, but nevertheless, that's the original idea. Now, of course, divergence of u is 0 in the core, so if you've got a wave-like motion, that means that u dot k is 0. And if you think about it, that means that k must be perpendicular to u, and since k is perpendicular to omega and b naught, that means the motions u, the velocities u, have got to be in the omega b naught plane. So wherever omega is, wherever b naught is, if it's some direction which is some angle to omega like that, of course those two vectors define a plane, and Brudzinski's idea is that the motions would be primarily in those directions. He called them plate-like because those two vectors determine a plate, and those are the directions, the preferred directions in which turbulent flows are likely to move. So it's extremely anisotropic. So in other words, it's a totally different picture from what you imagine in ordinary lab turbulence, where you get small eddies moving all over the place. Brudzinski imagines primarily small eddies moving in particular directions and particular plates, and much less transfer perpendicular to those plates. So, well, that's a problem. I mean, there are a number of people who are trying to make models in which the small-scale turbulence is parameterized in that way, with varying degrees of success. All the models I talked to you about before all have isotropic eddy diffusions in them. So they're essentially ignoring Brudzinski's idea. Yeah, as I said, there is quite a lot of modelling going on there. So that's another hot topic of research, to try and sort of correct that and have a look at the possible behaviours from anisotropic eddy viscosities to try and see what that actually might do. Okay, so again, the kind of turbulence that they're envisaging in the core is rather different from the conventional turbulence in the laboratory, where it's all driven by the inertial scale, going down from large scales to small scales, the Kolmogorov transfer process. In here, we're envisaging a situation where inertia plays a negligible role on the dynamo timescales and length scales, only on the very, very small scales that you end up with a spectrum. And the idea basically is that the instabilities, the turbulence is driven directly by convection and plate-like, so it's potentially something quite different. Okay, now let's just go back to these torsional oscillations I mentioned. So I told you that those things occur on cylinders, and here indeed is the cylinder drawn out. So that's the inner core, that's an imaginary cylinder. Of course, these things have no physical existence, they're just the cylinders on which the motions take place. And this one is centered on S, there, distance there, and of course that will have a corresponding ZB and a ZT, which can easily be worked out by Pythagoras. And we now come to J.B. Taylor's idea. J.B. Taylor's idea was, let's integrate over that cylinder the azimuthal equation of motion. And the reason he did that was because he noticed a lot of terms disappear if you start doing that. This term is 0 because there can be no net flow across that cylinder because of mass conservation. Whatever comes in has got to come out of that cylinder. If you go back a step, you can see that whatever comes out there has got to come back in there, so that there can be no net flow. So that's important. Coriolis term vanishes. The pressure is dP by d5. Take the phi component, of course, integrate dP by d5 around the circle, you get naught, because you get back to where you started. The Lorentz force doesn't vanish. The viscous force, well, that's pretty small in the core, as we've mentioned. E is very, very small. Most of the drag will be what's called suction. I don't want to go into that, but in a rotating fluid, most of the friction is actually at the boundary. And so it goes like e to the half, but even e to the half is jolly small. So that's a pretty small term there. And this thing, well, of course, this is essentially the torsional oscillation balance, because that's the Lorentz force integrated, and that's the inertia. But if you're looking on long time scales, you expect these torsional oscillations eventually to die out. So you would expect to be in a configuration where this integral either balances that, or because that's so small, that integral actually turns out to be zero. And this is J.B. Taylor's constraint. So on a long-term average, time-dependent things don't go, so on a long-term average we expect that integral of J cross B to be zero. J and B are not small, that integral is small, and the way that has to be achieved is by plus bits cancelling out minus bits. So the idea is that you take this integral and in some magic way the field that you get and the current that you get has got to have a zero average. So of course one can see, have a look at one's dynamo models to see whether that actually is the case. And of course it varies with time, so you only think that it will only vanish in a time average sense. And what people looking at dynamo models tend to look at is what's sometimes called a Taylorization. So that's the J cross B without unsigned J cross B, so the pluses and minuses can cancel out. And then you put a modular sign around there to have something to compare with, which of course can't cancel out, so it's got to be positive. And so what you hope is that TA goes to zero as the Ekman number goes small. And indeed it generally does, actually. I mean, the early simulations were rather large, only 10 to the minus 3, 10 to the minus 4, and they didn't really show much Taylorization. But in more recent simulations where E has got lower and lower, we're now getting to the state where that really is satisfied. So that remarkable condition, formulated in 1963 by Brian Taylor, really does seem to apply to the Earth's core. A little bit about zonal flows. I mentioned these zonal flows a bit before. So if you average the spiraling convections average to phi, you get an net acceleration produced by u dot grad u, which is the Reynolds stress. And in planets like Jupiter, where that drives this big zonal flow, much, much bigger than any of the convection flows that are actually existing. And the reason it gets so big is it's only balanced by a rather weak viscosity, so that even if u dot grad u doesn't have a huge average, it nevertheless turns out that you end up with a big u phi because it's got such a small friction to counterbalance it. This doesn't seem to happen much inside in geodynamo simulations. The reason being that the magnetic field also damps out such zonal flows. So the zonal flows in a dynamo have got to balance magnetic stresses, not just feeble viscous stresses, and those magnetic stresses are much larger, and those stop you getting a very large differential rotation. Interestingly, that's another sort of major difference between the Earth and the Sun. In the Sun, the zonal flows are huge, and the convection is very strong. The magnetic field is comparatively weak, and it doesn't seem to be able to stop the dynamo acting much at all. In fact, as far as I know, there's really not very much signal from helioseismology which corresponds to the solar cycle at all. In fact, so that the solar cycle seems to be having a very small effect on the differential rotation of the sun. That somehow is what you'd expect, given what we know about the magnitudes of B and J and the huge magnitude of U dot grad U on the sun. But in the Earth's core, where U dot grad U is very, very small, and the magnetic forces are relatively much stronger, it seems that things are locked together. I'll say a bit more about that in the next lecture. I've got a whole lot of sort of simulation results which sort of back that up. And other people also
So
seem
you
to
talk
find
about zonal flows, it's only in the phi direction.
Yes. Yeah. Yeah.
This language is not clear to me at all about it.
Okay, yes. So it's geophysical fluids language, isn't it? It's, yeah. A zonal flow is a flow, the average component in the phi direction. So you take out any non-axisymmetric components. So the U phi averaged over phi. That's what people are thinking about. And so zonal flows can be eastward or they can be westward, and in fact Jupiter is sort of eastward, westward, eastward in sort of bands. You know, the Sun has a zonal flow which is eastward in the equator and westward of the pole as it goes around faster at the equator, which is in some sense the most common and what you get out of simple convection.
And when one talks about a thermal wind, one means...
Yeah, well, I'm just about to get on. That's the next thing. So, the thermal wind is different. Thermal wind is produced by temperature fluctuations rather than the turbulence, the zonal flows. And to get a zonal flow, that's U phi is varying with Z. So that's breaking Taylor-Proudman constraint. So that's a U phi which varies with Z. And that's produced by a horizontal, or a latitudinal, I should say, temperature gradient. So that on the Earth, the pole is cold, as we know, being close to it now. The equator is still jolly hot, so that there's quite a big dT by d theta in the Earth's atmosphere, and that produces a du phi by dz, which increases as you go upwards, which is it's got to be nearly zero at the bottom because there's buildings and mountains giving you a friction at the bottom, but at the top you end up with a huge zonal flows, and that's why it takes less time to get from America to England than it does to the other way, if you see what I mean. It's because this is a huge jet stream that's produced by this, the very, very fast jet stream. And in the Earth's atmosphere, it's massive. I mean, it circulates once every 23 hours rather than once every 24 hours. It's a sort of order one differential rotation. In the core, we expect the same kind of thing, but it goes sort of the other way around. If you go to the Earth's core, we expect the poles to be warmer than the equator, because a lot of the latent heat is released from the inner core, and we also expect it to be lighter because the light material is being released from the inner core boundary, and before it actually gets out to the outer side of the tangent cylinder, it will be stuck inside the tangent cylinder. So we expect anticyclonic polar vortex. Okay, this actually, you may have heard about some of the calculations where the inner core rotates more rapidly than the mantle. Some of the first simulations showed straight off that the inner core typically is rotating faster than the mantle, and that's essentially exactly this effect here, because it's going anticyclonic up there, so relatively it's going cyclonic down at the bottom, so that means the bottom turns around faster. Okay. And that again is that's again something which is a very active topic of research. Right, I've just got a bit of time to talk about scaling laws. So what have we seen from all these linear calculations and the wave discussions? Well, we've seen that inertia, Coriolis, buoyancy, Lorentz, and viscous forces can all be important in different regimes. And what we really need to know is, in strongly nonlinear convection, in the circumstances that are going on in the Earth's core, how do these things actually balance out together? It's easy to do this in terms of linear theory, but what actually happens when you get to strongly nonlinear calculations? And we're trying to use sort of physical intuition combined with simulations to try and work out exactly how this is actually operating. Because what we'd really like to know is what typical velocities and magnetic fields are actually being generated from a given heat flux. so that if we have new planets, we can estimate what's going to happen in those new planets. Newly discovered planets, which ought to be able to work out what magnetic fields and typical flow speeds in the cores are, and indeed to find out what the typical flow speeds actually are in our own planets, which are hidden from view directly. Okay, so let's think about this one. Well, the beginning of nearly all these theories is to estimate the temperature fluctuation and the velocity fluctuation from the convective heat flow. So the convective heat flux is given by that formula. So to a simple approximation, I'm just going to replace these things here by a typical velocity and a typical temperature. Now, even that very simple formula has controversial elements in it. In convection, generally hot fluid rises, okay? So generally one expects that the hot fluid, i.e. the high temperature fluid, will be strongly correlated with UR, so that you would expect the correlation coefficient in that integral to be close to 1. However, we are talking about rapidly rotating convection, and anybody who knows has seen laboratory experiments of rapid rotation knows that having started to move in one direction, the fluid got a horrible tendency to suddenly turn sideways on you and move sideways, so that it's actually not entirely clear that this is strongly correlated. There may be a correlation coefficient which is significantly less than 1, but I'm going to ignore that, and I'm going to assume, for simplicity, that hot fluid rises. Okay, so then I can replace basically the convective heat flux by the typical velocity times the typical temperature fluctuation. And that incidentally gives me straight away an estimate of the typical temperature fluctuation inside the core. You might say, how on earth do we know what the typical temperature fluctuation inside the core is? Well, we know this in terawatts, or in watts per, actually that watts per square metre actually is the unit for that. We know what that is, we can make a pretty good guess at that. We know that roughly from the westward drift, so from those magnetic observations I talked about. So you can work out this, and the answer comes out to be something like 10 to the minus 4 of a degree centigrade. So typical temperature fluctuations in the core, as I mentioned before, are really, really tiny. It's so close to isothermal, it's unimaginable. But those temperature differences, those tiny temperature differences, are actually what's driving the whole thing, the whole dynamo. So that gives us an estimate of T star in terms of the convective heat flux. And then we've got to start thinking about what forces are going to be important in the equation of motion, because that's crucial to understanding the velocities that they're going to achieve. Now, remember what terms we actually had in all this thing. I'm going to take out the pressure because it turns out that when we take the curl of these equations, the pressure drops out, and so that suggests that it plays a less important role. The sort of simplest sort of balances you might imagine, well, let's forget viscosity, it's very small in the core after all. So we might think maybe inertia might be important, buoyancy might be important, and then if you imagine that buoyancy might be important, well, you can estimate the buoyancy in terms of heat flux using this formula here to eliminate T prime. So if you balanced inertia against buoyancy, what would you get? You get an equation which would have U star cubed in it, and this is basically the mixing length formula. So that is basically what you'd expect in strongly nonlinear convection, and it's pretty close to what actually happens if you actually measure laboratory experiments. This was done a long time ago, back in the early 60s. People measured this at something called the Deardorff velocity. I quite like that name because he was the first person to clearly come up with that formula. And so that tells you, that gives you a formula for the typical velocity in a convecting system in terms of the heat flux, which is the physically relevant, unmeasurable quantity in core convection. Okay, so if you try that, let's just try that, well, you end up with, it's not bad. I mean, you don't end up with a crazy answer, but it is actually too fast. You end up about a figure about 10 times too big. And that suggests that rotation and magnetic field is actually slowing down the convection in the core. So even that would produce a pretty slow speed, but we think it's even slower than that from the westward drift measurements. This theory seems to date back to papers in the 1980s, certainly, possibly even some of it a bit earlier, to Ray and Hyde's work. We take the vorticity equation, so that's the curl of the equation of motion, and we're going to look at, so we're going to look then at this then turns, the Coriolis then turns into omega dot ground u, and of course that's the derivative in the z direction, which is of course rather small, and that's the Taylor-Proudman theorem, because you have motions which have a short length scale in z, that becomes huge and unbalanceable by anything else. And then this will give us some kind of measures, balances on that, balancing against that, balancing against that, and we ignore that for the time being. That seems to be, that's quite surprising because we think the Lorentz force is important, but that's what I'm going to do. Because we have these tall, thin columns, the length scale across the column is clearly small, so I call that L perp, and the length scale along the column is large, so I call that D. So D is something like 2,000 kilometres, and L perp is the direction across the rolls, which might be something of the order of, well, we don't really know to be honest, but some tens of kilometres. So then we get a balance like that. But actually, this actually yields a formula for L perp if you actually solve these, because we can eliminate T prime using the convective heat flux in terms of U star. So then this gives us two equations, one of which for U star and L perp, and you can actually solve these specifically. So you get two answers coming out of here. And if you do that, you get an answer which is, and that gives you, this formula here. That's how we solve that, which turns out to give you a typical length scale of only about 4 kilometres, and that's sometimes called the Rhines length, because it's the length scale on which inertia and Coriolis balances. Okay, so if we now try to get the convective heat flux into that, we get this formula down here, and we actually get an estimate for U star over omega d, that's the Rossby number, in terms of the convective heat flux. And Ole Christensen has called this a sort of convective Rayleigh number, he denotes this by R and Q, and so the formula then says that the Rossby number goes to this power to the 2/5. So that's the simple estimate you get if you just make these crude balances. Okay, so this is basically, that's a consequence of that plus the convective heat flux relation. And rather remarkably, if you actually look at dynamo simulations and plot a lot of different dynamo simulations and plot the value of R at Q against R at O, you get a remarkably good fit for the power law relation, and the best choice of exponent is about 0.41, which is extremely close to this 2/5. So that does really seem to be actually what's happening in the dynamo simulation, that balance, which is actually occurring. So that's sort of interesting because it's telling us that the column thickness is ultimately controlled not by the viscous scaling of e to the 1/3, but by the nonlinear scaling of the balance between inertia and Coriolis. Or more precisely, it's the vortex advection compared with vortex stretching. And that's the physical balance which is going on there that determines this 4 kilometre length scale. But that has ignored the magnetic forces, that's ignored the Lorentz forces, and in most of the simulations, as you can imagine from a good agreement between that, the Lorentz forces don't seem to be doing very much to the convective velocity, so they don't seem to be affecting that roll thickness very much, which was a bit of a surprise to me and to others, because Lorentz forces can thicken the columns, as we saw from the linear results. So the question was, why don't they do that in the simulations? And the answer is that it can be these things, these magnetic convection calculations can sometimes be useful. You've got to remember that they're for uniform imposed magnetic fields. Of course, the motions inside the core churn up the field, put it into sort of big ropes, strong areas, and there are probably holes that can develop inside that flow where you can get comparatively thin columns actually going. So maybe there's a non-uniformity of B, which is different from a theory where it's assuming uniformity, you could be actually really rather important. Okay, so typical core velocities, they put the numbers in, you get this incredibly small value of the heat flux, and this dimensionless form here, where you've got the heat flux and rotation values over there, it turns out this is extremely small, but it does turn out to give you a sensible value of the convective heat flux with the usual estimates of Cp. So it all sort of, the scaling certainly hangs together in the sense that it gives you sort of sensible numbers for the velocity, it gives you sensible numbers for the heat flux. Okay. So that's the, as I say, that's a little sort of gloss on all that. That, of course, just had the heat flux. You can do the same kind of calculation for the compositional convection. And as I mentioned, the inner core is probably not that old, only about 1.5 billion years, considerably less than the age of the Earth. And that gives you this mass flux, about 31,000 kilograms are being liberated of light material per second, and that gives you a value of RAKQ, but that's not all that different from the previous one, and so that all seems to work out quite nicely. I was always a bit worried about this, and so was Sergei Starchenko, because we never really believed in this 4 kilometre length scale. We think the magnetic field will stop things before you get down there. So we worked out what the consequences would be if that actually happens, if the magnetic field does actually get a grip on the roll size before you get down to 4 kilometres. It doesn't actually do much to that scale. All it really does is turn that 2/5 into a 1/2, which is not all that different. So it doesn't actually change the answers hugely. So actually, I would argue that means that we can't rule out that there's some kind of Lorentz takeover at very low values of RAQ, because that would be consistent with the data, just like the previous calculations are consistent with the data, because it doesn't change the answers that much. So I would say that the jury's still out on that one. Okay, so now we've got an idea of what sort of fluid velocities are going on. Well, I should say, let's give you an idea, that's sort of 10 to the minus 4 metres a second in the Earth. You know, what's Jupiter? Turns out it's about 10 to the minus 3 metres a second, so it's about 10 times faster. So right in the interior, magnetic interior of Jupiter, the flows are really quite slow too. I mean, that's quite surprising when you think about 100 metres a second going around on the outside, but that's the outside. This we're talking about is the magnetic core, where the dynamo is actually being produced. And there have been flybys of Jupiter's magnetic field, and we can sort of see how it's changed between Voyager and Galileo. That's about 25 years. And the changes that we see in the magnetic field are consistent with 10 to the minus 3 metres a second. So there is some external confirmation that that's actually correct. So I'm sort of reasonably happy about that estimate, actually, that velocity estimate. I think it probably will work in other planets too. Now we come to the vexed question, how to estimate the magnetic field strength. Now we've already had Candu talked a little bit about his formula about omega dot omega and J dot B in the mean field, alpha effect and the saturation and so on. Well, that's sort of one way of doing it. This is a slightly different way of thinking about it that comes from the core, but it's sort of related actually. Like all these things are. Basically, remember that the magnetic energy is much greater than the kinetic energy in the core, so that simple equipartition arguments like half rho u squared going like b squared, half b squared over 2 mu, that's not going to get you the right answer. That will get you an answer of magnetic field much too small if you don't use that. It's just incompatible with observations at all. So that's not going to work. So what do we do? Well, what do we do? I think these ideas really came from Christensen and Tilgner. we start by saying that the rate of working of the buoyancy forces has got to exactly balance the ohmic and viscous dissipation. That's an exact interval that you can write down from the equations, the fundamental equations of motion. And the rate of working of the buoyancy forces can be related to the convective heat transport, convective heat flux, through an integral, which is quite nice. So this actually works even in compressible flows, as well as in Busenest flows. So we can therefore get an estimate of the rate of working of the buoyancy forces in terms of the convective heat flux, which is the quantity we think we know a bit about. So that means that we can make an estimate of that. So we think we know what the sum of the viscous and the ohmic dissipation is. So then comes the question of how do you split the ohmic and viscous dissipation? Is it the same? Is one bigger than the other? Is the other bigger than one? I think Agris Galaitis in his talk mentioned that this one is actually considerably bigger than that one in his experiment. In the simulations, they tend to be, when you get down to small e, they tend to be quite comparable. There's a sort of long-standing viewpoint, which has really been dignified by age rather than any intellectual content, which suggests that that ought to be larger than that, ultimately, that in the core, because the magnetic field is much bigger, somehow then the ohmic dissipation ought to be larger. It's not a very good argument, actually, when you start to look at it in detail. But somehow these got to be split. The assumption we're going to make is that this is at least the same size as that, and it may be bigger than that. So basically we're going to balance this against the ohmic dissipation. So we're going to assume that the viscous dissipation is certainly not an order of magnitude bigger, but comparable to this. And that's what you need to do to make progress. And as I said, that's reasonable from the point of view of the simulations, where typically you get this is roughly similar to that. But again, it's an interesting question, of course. So that means we can estimate that, because we know what the convective heat flux, so we can estimate that. But that, of course, doesn't unfortunately tell us what B squared is. It tells us what J squared is, because that's the ohmic dissipations in terms of the square of the currents. So how do we get from this to B squared? Now here we have to have an additional piece of information, and I'm going to talk about the Christensen, it's what I call the Christensen-Tilden law. This is a paper, a 2004 Nature paper, and they pointed out that in a lot of simulations this is true. That's the relationship between the magnetic energy and the ohmic dissipation, which that relation is essentially a time, because it's the time essentially that the magnetic energy would take to dissipate away, yeah, and so that's the dissipation rate. So dissipation rate times the dissipation time is what the magnetic energy. And basically, their idea is that the dissipation time scales in this way with that there's a dissipation, there's a current length here, that delta B can be related to the current and the magnetic field that tend to have a length scale, because the curl of B is essentially J, so that B over a length scale is J, and their idea is to take that length scale as that which is essentially Rn to the half. So basically what they're saying is that the length scale is the order Rn to the half. It's also equivalent to the thing which I think Alvar yeah. It's also essentially equivalent to this thing, actually. No. It's the one where you have the turbulent. You pointed out that the dissipation time, was not dependent on the magnetic Reynolds number. It was independent of the magnetic Reynolds number. So another way of saying this is this dissipation time is the typical velocity divided by the typical length scale. Not our way around the typical length scale, L over U. So that's another way of putting that formula, and it's essentially equivalent to saying the length scales over which the current is dissipating is Rn to the half, which is consistent with the idea that it's sort of what the field is expelled into flux shapes, flux shape thickness of the field of Rn to the half.
Usually you get such a scaling when the stretching balances dissipation.
Yeah. Yeah, I think that's right, and I think that's what we think is actually, that is probably what's actually happening in these dynamo simulations. Certainly. I mean, how universal this law is an interesting question. I mean, because until they pointed out they seem to fit reasonably well with experiments, I think they fitted it to the Carter experiments. They pointed out the obvious sort of correlation. And, of course, I mean, on the smaller scales, you would expect the dissipation time to be shorter. Again, so it's not very much reasonable. How accurate it is, one doesn't know. But one, of course, gets now, if you know now the dissipation time, so now we can work out in terms of Rm the ratio of that and that. And since we think we know that, we can therefore work that one out. Okay. And if you do that, so you've got e to mu j squared, that's the dissipation rate, is essentially that, which now becomes that over delta B squared, and that's got to balance the heat flux, because that's got to be equal to that, so we've got that balancing that, and we've got a formula for delta B, and so you bung that in, and that gives you an estimate for B in terms of the heat flux, which turns out to be that. And that, of course, has got the typical velocity u star, because that's got the Reynolds, that's got the u, that's the u star that Anvar had in his theory, where the dissipation time is a d over u star, so that's basically another way of putting that. So we get that formula for B star, and putting the typical velocity estimate into it, we get this grand formula for the magnetic field strength inside a planet. Okay, so that tells you what we think the magnetic field strength inside the planet actually is going to be if all those scaling laws are actually correct. So, yes.
But with the heat flux, most of it goes through the surface, the outer surface, isn't it?
Quite a bit of it does, yes. I mean, if you remember, I did give a fairly lengthy, perhaps not too coherent explanation of the relationships between the convective heat flux, the magnetic dissipation, and the total heat flux through. And yeah, I mean, there's this Carnot efficiency factor is basically what you're referring to. So this is the thing which turns out to be about 10% in the core. So there is that factor. But I'm taking that into account. I'm assuming that the F here is really the convective heat flux rather than the total heat flux that's coming through. So this is going to be less than the 10 terawatts. It's going to be probably only half terawatt or 1 terawatt. Yeah.
Can it be turned around, these arguments, when there's a reversal, what happens to the heat flux?
Well, that's an interesting argument. I mean, remember, these are only orders of magnitude estimates, really, of the field. I mean, the whole thing has really got to be scaled, so I wouldn't want to.
But this tau, how long was that again? That's probably also comparable to the duration. I mean, reversal time.
It depends on the length scale of the individual J's, of course. But it's basically Rm to the 1/2 times the dissipation length scale. So it's turned out to be hundreds of years.
So that's comparable to the reversal time.
No, it's shorter than reversal. It's very much shorter than reversal.
Yeah.
Definitely shorter. It's related to the viscous, to the fusion time, magnetic diffusion time. It's that times the Rm and a half.
Even from the phenomenology, if the dot ball goes down, what's holding the columns to be the fat things you need?
Well, for a start,
discussion for you.
yeah, that's quite a complicated question, but in the simulations where most of this is being tested, the magnetic field is not actually doing a huge amount to the column thickness. So the column thickness, even when the magnetic field goes down, the columns get typically a bit thinner, but they don't get usually thinner, so it doesn't make a huge difference. But I just want to know, just to finish off, the most interesting thing about this formula, I think, is that obviously it goes up with the heat flux like natural. The more it's driven, the stronger magnetic field you'll get. But it's the amazingly weak dependence on rotation. So this theory, if correct, would suggest that in different planets the rotation rate hardly makes any difference to the magnetic field strength expected. So that if Venus had a dynamo, which it doesn't probably for reasons of the fact it hasn't got mantle convection, if it did have a dynamo, even though it rotates very, very slowly, you'd expect it to have a magnetic field strength comparable to the Earth's magnetic field, despite the fact that it rotates very, very much more slowly. And that is quite a new result. I mean, if you look at the sort of history of how people have thought of B scaling with omega, almost everybody has thought that B would scale quite strongly with omega and be much larger with large omegas. So this is sort of new in the sense that this is producing answers where B is only scaling rather weakly with omega. Probably time to stop.
Thank you.
So that formula is confirmed by Christensen's calculations, right?
That formula, yeah, that fits very nicely with the simulation.
Glasmeyer's also?
Yeah, I think it's fair to say that that fits with most of the simulations, but of course remember all the simulations have got, they're all for moderate Reynolds number, they're all for Ekman numbers which are much larger than the real thing, etc. So there is a range of parameters in these simulations, but it's nothing like as huge as one would really like. But it fits quite nicely. So it does seem to be what's actually going on in these simulations. And certainly that Christensen, Tilden, and the law seem to be backed up quite nicely in the simulations too. So, yeah. There is some backing for that.
Right. Okay, other questions? I mean, this, by the way, is slightly different from what we then normally expect for the Sun, because this is more proportional to the Dyrdek velocity.
Yeah, that's right.
Yes.
Yeah.
What will get wrong here in the Sun? The
Uh,
Sun will be different, right?
The Sun is different. For a start, the
No,
velocity,
it's the same, actually.
the velocity
It's the
scale.
same.
Usually, what you get is the mixing length theory. Yeah.
That's what
Okay, so that would have a U which scales essentially like the heat flux to the 1/3, which is classical mixing length theory. So I've got a steeper power on that, 2/5 or a half, yeah, depending on your taste. So that's one difference. But the main difference is really, I think the huge difference would be the assumption that the dissipation is ohmic dissipation. I think if you look in the Sun, you will find that the ohmic dissipation is probably extremely small compared to the viscous dissipation because of a huge amount of turbulence. So the magnetic field is sort of a bit part player in a sense in the Sun. Basically, I don't believe. I mean, apart from sunspots, yeah, which occupy only a tiny fraction of the Sun, even when there are any. Most of the surface of the Sun is unaffected. The convection is unaffected by the magnetic field. So whereas here we're making the assumption that basically that the dissipation is primarily through ohmic.
But isn't that it's a flux?
Yeah.
And, to the 1/3 power, and that is your RMS velocity.
Yeah.
So that really just means that the magnetic field is comparable to the RMS velocity of the turbulence, and that's what we really have in the Sun.
Yeah.
So actually it is the same.
It certainly relates. I mean, it certainly relates. I mean, there was also the paper, a recent paper, you've probably seen it, which plots essentially this thing here, for rapidly rotating stars and the Sun and the planets all on one diagram. And rapidly rotating stars, this formula works reasonably well. The Sun falls somewhat below that line, in fact quite a bit below that curve. The field strength in the Sun is actually quite a lot weaker than the field strength you get from that formula. But for rapid rotators, which typically have a much higher, much bigger star spots than the Sun, have much stronger magnetic fields, and there this formula doesn't do too bad a job. So for them, it may well be true that the ohmic dissipation is important compared to the viscous dissipation, and convective heat flux and therefore be related through this, and these formulas will actually work.
Any other question?
Still, also just said that there is a RMS velocity here. But still, Chris, do I understand correctly that this is a super Scottish magnetic field? Here, magnetic energy is larger than kinetic energy.
It's a very strong super. That's it. It's not an equipartition argument. No, this field is.
And the source of magnetic energy is thermal flux.
We had one time to talk to Chris during the group meetings. Let me did change it here, I thought. And so here's the schedule. Let me try and make it then fit. So we have this on the web. If you forget this, you can pick it up on the web page again. To remind you again where you find it. It's on this page under additional information down here. Then you go to lectures in temporal order. Then you look for today, which is here. And there's a list. And so we have, again, 4 different groups. They're all different from the previous ones, except that Mr. Jones is with us. I chose to be one of the participants myself today, in order to alleviate the duties on the other participants who had already 2 group sessions. So Agnes and Chris will go to house 12. And you know where that is? Yeah. And Piali will go with you to that house. And then I will go together with Jean-François to house 13, the main building, and we will swap in after half an hour. It's 4:30, and then after that time is over, we will swap houses, and Chris goes from the large seminar room to the large seminar room in house 13, and small goes to small. Straightforward. Questions? Okay, then see you then.